Linear Algebra, Lecture 20. We only have 6 more lectures in the course, actually. So you asked in section 4.4, number 1. And this is on change of basis. So let's start. Let me just make sure I'm looking at the right problem. So in the vector space R2, we have 2 sets of vectors. The set F consists of the vectors 1, 3, and 2, 7. And the set G consists of the vectors 2, 0, and 1, 1. And the first part is to prove that F and G are both bases for R2. So R2 has dimension 2. So every set of 2 linearly independent vectors is a basis. So it's enough to prove that these 2 vectors are linearly independent and these 2 vectors are linearly independent. So let's start with the easier one first. Let's look at G. So suppose X times X1 times, just say X times 2, 0 plus Y times 1, 1 equals the 0 vector. See, what is this vector? This is 2x plus y, y. So this equals 0 if and only if y equals 0, and 2x plus y equals 0. But if y is 0, this means 2x is 0, so this means x is 0. So these 2 vectors, the vectors in G, is a linearly independent set of vectors, and therefore it's a basis for R2. Okay, so is there a question about this? This is, no, you just have to prove that each of these sets is by itself is a basis. So 2
So
vectors. Yeah, go ahead.
I thought after proving that these 2 vectors are linearly independent, we had to do something more to prove it.
No, so that's a very good question. So suppose we have a vector space V, and the dimension of V is equal to n. Let V be a set of n vectors that are linearly independent. Right? So this is a subset of V. Suppose we let W be the subspace of V generated by this set V. So we have the vector space V, and we have these n vectors, V1, V2, up to Vn, and they generate a subspace W. I claim that W, in fact, is all of V. That is, that this set must generate all of V. If not, then W is a proper subset of V. So there's some other vector, let's call it Vn plus 1, which is in V, but not in W. But then the set of vectors V1, V2, up to Vn, and then throw in Vn plus 1, is linearly independent. Because if some linear combination of these was equal to 0, the coefficient of Vn plus 1 couldn't be 0, or else it would be in W. But this is impossible, because the dimension of a vector space is the size of of the maximal subset of linearly independent vectors in the space. So you can't have n plus 1 linearly independent vectors in a vector space of dimension n. A basis is a set of linearly independent vectors that generates the subspace. The size of every basis is the same, and that number of vectors in the basis is the dimension. And any set of n independent vectors in an n-dimensional space must generate the space. Otherwise, there would be an additional vector that's linearly independent of the previous ones. So it suffices to show these are linearly independent. So let's look at the second set, 1, 3, and 2, 7. So suppose x times 1, 3 plus y times 2, 7 is the 0 vector. This is x plus 2y, 3x plus 7z. Sorry, 3x plus 7y. So x and y satisfy the equations x plus 2y equals 0, 3x plus 7y equals 0. This says x is minus 2y. If you plug that in here, 3 times minus 2y plus 7y is 0. But this is 7y minus 6y. This is y. So y is 0. And if y is 0, x is 0. So these two vectors are linearly independent, and so f is also a basis. So we can write every vector in a unique way as a linear combination of the vectors in F, and also in a unique way as a linear combination of the vectors in G. And so if you take any vector in V, right, there's a coordinate vector for V with respect to the basis F. Let me see what notation I've been using here. So if this is x1, x2, this means this is the same as saying that the vector V is x1, f1 plus x2, f2, where f is the set of f1 is 1, 3, f2 is 2, 7. So these are the coordinates. This is the coordinates vector for any vector v with respect to f. And you can also write the coordinate vector of v with respect to the basis g, called out y1, y2, which means v is y1, g1 plus y2, g2, where g consists of g1 is the vector 2, 0, and g2 is the vector 1, 1. Right? And there exists a change of basis matrix, say P, such that if you, and this is going to be a 2 by 2 matrix, such that P applied to the column vector, the coordinate vector for V with respect to F, gives you the coordinate vector for V with respect to G. And the way one gets that is as follows. Let's write G1 and G2 each as linear combinations of F1 and F2. So I want to write, let's see, let me just do it in general, and then I'll work it out in this particular example. Suppose G1 is some P11 F1 plus something times F2. Do I want to call this P12 or P21? P21 F2. And G2 is some linear combination of F1 and F2, P12 F1 plus P22 F2. So F1 and F2 form a basis for my vector space. So I can write each vector G as a linear combination of them. So what does this mean? Suppose I have a vector V, which is some linear combination Y1 G1 plus Y2 G2. That's Y1 times P11 F1 plus P21 F2 plus Y2 times G2, which is P12 F1 plus P22 F2. This is some linear combination of F1 and F2. It's P11 Y1 plus P12 Y2 times F1 plus P21 Y1 plus P22 Y2 F2. This is exactly what you get if you take, let's see, if I had the matrix P, the coordinates P11, P12, P21, P22. What does P apply to the vector Y1, Y2? That's P11, P12, P21, P22 times Y1, Y2. This is P11, Y1 plus P12, Y2. That's the first coordinate. The second coordinate is P21, Y1 plus P22, Y2. That's exactly these numbers. So if I take this matrix P, apply to the coordinate vector for V with respect to G, that's P of Y1, Y2, that gives me this, which is the coordinate vector for V with respect to the matrix F. If you write V, sorry, with respect to the basis F, if I write V as a linear combination of F1 and F2, these are the coordinates. So this P is the change of basis matrix from G to F. So in our case, where F is the basis that consists of the vectors 1, 3, 2, 7, and G is the basis that consists of the vectors 2, 0, 1, 1. To compute the change of basis matrix, I have to be able to write each vector in G as a linear combination of the vectors in F. So I want to write 2, 0, that's my G1, as some linear combination of F1 plus F2, that's some number P11 times 2, 0 plus P21 times 1, 1. What is this? This is P11 times 2 plus P21, P21. So P21 I'm sorry, F1 and F2 are 1, 3, and 2, 7. So I want to write G1 as a linear combination of F1 and F2. That is P11, 1, 3 plus P21, 2, 7. That's P11 plus 2 P21, 3 P11 plus 7 P21. In other words, I have to solve two equations and two unknowns. P11 plus 2P21 equals 2. 3P11 plus 7P21 equals 0. So any way you want to solve it is okay. If you use, for example, the determinant formula, the determinant of this matrix, of the determinant of P, which is the matrix P11, P21, sorry, not the determinant of the matrix P, but the determinant of the coefficient matrix of this system of equations is 1 times 7 minus 2 times 3 equals 1. So the denominator in the determinant formula for solving two equations and two unknowns is this is the determinant of 2027, which is 14. P21 is the determinant of 1320, which is minus 6. So let's see if this works. 14 minus 12 is 2. 42 minus 42 is 0. So this is P11, this is P21. Those are the coefficients here. The matrix P, this is going to be 14 minus 6, first one. Sorry, P11, P21, 14 minus 6, there's first column. Next, we want to write G2, which is the vector 1, 1, as a linear combination of F1 and F2. This will be P12 F1 plus P22 F2. That's P12 times 1, 3 plus P22 times 2, 7. This is P12 plus 2P22, 3P12 plus 7P22 equals 1, 1. Again, so we're solving two equations and two unknowns, and using, again, the determinant of this coefficient matrix is 1. So P12 is the determinant 1, 1, 2, 7, which is 5. P22 is the determinant of 1, 3, 1, 1, which is minus 2. So let's just check. If I have 5 and minus 2, 5 minus 4 is 1. 15 minus 14 is 1. So this is 5 minus 2. So this is the coefficient, is the change of basis matrix for this problem. Now, you might say that's a lot of work and a lot of calculation, and that's true. Sometimes there's a lot of work and a lot of calculation. So if we're lucky, we did everything right, and this really is the change of basis matrix. So one way to check, so this is, let me turn back to the problem. Compute the coefficient vectors for the vector 5, 3, the coordinate vectors for the vector 5, 3, and show that we have the right matrix. So again, that me F is 1, 3, 2, 7. This is F1, this is F2. G is two vectors, 2, 0, 1, 1. And I want to write V, so this is part C. V is the vector 5, 3. So I want to compute the coordinate vector for V with respect to F, and I want to compute the coordinate vector of V with respect to G. So if the coordinate vector for V with respect to F is x1, x2, this means that 5, 3 is x1, f1 plus x2, f2. That is x1 times 1, 3 plus x2 times 2, 7, which is x1 plus 2x2, x1, 3x1 plus 7x2. So I want to solve for x1 and x2. X1 is going to be the determinant of 5, 3, 2, 7, which is 35 minus 6 is 29. And x2 is going to be the determinant of 1, 3, 5, 3, which is minus 13. So if this is correct, let's just check. What is 29F1 minus 13F2? 29F1 is 29 times 1, 3, minus 13F2, which is 2, 7. So this is 2987 minus 2691. That is that right? Not quite right, because I get, in fact, it's completely wrong. So let me just double check. So I want to write 5, 3 is a linear combination of 1, 3, and 2, 7. So 5 is going to be x1 plus 2x2, and 3 is 3x1 plus 7x2. So I'm solving two equations and two unknowns, and x1, let's see, should be the determinant of 5, 3, 2, 7. That's 35 minus 6 is 29. And x2 should be the determinant of 1, 3, 5, 3, which is 3 minus 15 is minus 12. So let's see if this makes a difference. I'll make this 12. So this is 29 times this minus 12 times that. That is equal to 2987 minus 2484, and that is 5, 3. So that's correct. And then I want to find, for the vector 5, 3, the coordinate vector for V with respect to the basis G. So this is y1, y2, if and only if what? V, which is 5, 3, is y1, g1 plus y2, g2. That's y1, 2, 0 plus y2, 1, 1. That's 2y1 plus y2, y2. And this means that y2 is equal to 3. And if this is 3, y1 is equal to 1. Right? Let's check. If I take y1, g1 plus y2, g2, That's 1 times 2, 0, plus 3 times 1, 1. And lo and behold, that is 5, 3. So that also checks. So I've done by brute force calculation that for the vector v equal 5, 3, the coordinate vector for v with respect to f is 29 minus 12. And the coordinate vector for v with respect to g is 1, 3. And my change of basis matrix P, the matrix that satisfies the property that v applied to the coordinate vector for v with respect to g is the coordinate vector for v with respect to f. That matrix P that I calculated 15 minutes ago was 14 minus 6, 5 minus 2. So let's check. We have to check this equation. So P VG is 14 minus 6, 5 minus 2, applied to the vector 1, 3. That's 14 times 1 plus 5 times 3, minus 6 times 1 minus 2 times 3. That's 14 plus 15 is 29. Minus 6 is minus 12. And lo and behold, there is some justice in the world, and we got what we're supposed to get. Okay. So P is the coordinate, is the change of basis vector from the basis G to the basis F. Now, there is also a change of basis matrix Q from F to G. So this matrix Q will have the property that Q times the coordinate vector of V with respect to F is the coordinate vector for V with respect to G. And in fact, it's the case that Q is P inverse. So P is this matrix 14, 5, minus 6, minus 2. And we want the inverse of that. And we actually have a formula for the inverse of a 2 by 2 matrix. It's 1 over the determinant of P times the matrix you get by interchanging the main diagonal elements, minus 2, 14, and changing the sign of the off diagonal elements, minus 5, 6. The determinant is minus 28, minus 30 is 2. So this is a half. So if you multiply this matrix by a half, you get minus 1, 3, 7, minus 5 halves. That's what it is. And let's just check if you apply Q to the coordinate vector of V with respect to F. This is the matrix Q, minus 1, minus 5 halves, 3, 7. The coordinate vector of V with respect to F was 29 minus 12. So when you multiply this, you get minus 29, minus times minus is plus, 5 halves of 12 is 30. 3 times 29, which is 87, minus 84. This is 1, 3. And by a miracle, 1, 3 is exactly what it's supposed to be. So I managed to do this problem without making too many mistakes, but this is what's involved. Right? This is computing the change of basis matrix in this example.
How did you compute the change of basis P?
So if you look at the text, you will see, I believe it's on page 220, theorem 413. It says that V be an n-dimensional vector space over the field F, that F be an ordered basis for V, that G be an ordered, an ordered set for V. Sorry, that's not what I wanted. That's a simple criterion. Let me find the formula. Yeah, so on page 223, theorem 4.14. So let me just write it down if you don't have the book handy. So this is on page 223, theorem 14. So we have V as a vector space. The dimension of V is n. And we have ordered bases, two of them, script F. So it consists of the vectors F1, F2 up to Fn, and a basis G consisting of the vectors G1, G2 up to G sub n. So you can define the n by n matrix P, the coordinates Pij, by, you write each G sub j as a linear combination Pij F sub I goes from 1 up to n. And the matrix, the n by n matrix Q with coordinates Qij, by the similar formula, you express each vector Fj as a linear combination Qij G sub I goes from 1 up to n. And then the theorem says these are the change of basis matrices. If you take P and multiply it by the coordinate vector for V with respect to G, you get the coordinate vector for V with respect to F. And if you take Q times the coordinate vector for V with respect to F, you get the coordinate vector for V with respect to G. So these are the formulas for computing these two things. And in fact, it's easy now to check that P times Q and Q times P are the identity. That is, each is the inverse of the other. Because, for example, G sub j is summation Pij F sub I goes from 1 up to n. But this is summation I goes from 1 up to n. Pij, let's see if I can write, this changing the notation slightly. So F sub I is summation k goes from 1 up to n. Q ki G sub k, right? This is just, so I can plug that in here. This is summation k goes from 1 up to n. qki g sub k. If I interchange my summations, this is summation, k goes from 1 up to n, summation I goes from 1 up to n, qki pij times g sub k. And because the vectors g are linearly independent, this is equal to 0 if k is different from j, and 1 if k equals j. So this is delta kj, Kronecker delta, which says exactly that q times p is the identity. And you can get the opposite, p times q equals the identity, by writing fi here, fj here, and then expanding in that way. But that's where this is the basis of this is the theory. I mean, I'm not going to ask you to prove the theorem, but you have to know the theorem and be able to use it. So on an exam, if I give you a basis, if I give you two bases and ask you to compute the change of basis matrix, that's a calculation you have to be able to do. Okay. Any other questions about this? I mean, there are a lot more homework problems which give you the opportunity to practice a lot doing these calculations. Okay. We talked previously a little bit about linear transformations. And I'm going to say some more about them now. So we have vector spaces over the same field, V and W. Right? A function T from V to W is a linear transformation if it satisfies the following two properties. First, for all vectors V and V prime in T, T of the sum of the two vectors is T of V plus T of V prime. So, and for all vectors V in the vector space and scalars C in the field, real numbers or whatever, T of C times V is CT of V. So these are the two properties that a function from one vector space to another must have to be called a linear transformation. And in the special case, when V is equal to W, so we're looking at functions from a vector space V to itself. In that case, T is called a linear transformation. T is called a linear operator. So this is just language. And the world is full of linear transformations. So for example, the map I from V to V defined by I of v is equal to v is a linear operator. It's called the identity map, or the identity operator, or the identity linear transformation. Why is it a linear transformation? Because I of v1 plus v2, this is the identity. It's v1 plus v2, but of course I of v1 is v1, and I of v2 is v2. And I of c times v is c times v, but v is I of v. So these two properties are satisfied for the identity function. We also have the zero function. Let's call it zero from v to w, where zero applied to any vector v is the zero vector. So why is this a linear transformation? 0 of v1 plus v2 is 0. 0 is 0 plus 0. 0 is 0 of v1, and 0 is also 0 of v2. So this property is satisfied, and 0 of c times v is 0, which is the scalar 0. Sorry, yes. C of c times v is 0, which is c times the vector 0, which is c times 0 of v. It's kind of simple, but you have to be careful when you write it down. Let's look at some other examples. Suppose I have t from R2 to R2 defined by t of xy is x0. So if you think about this geometrically, what does this mean? Here in R2, you have the vector xy, and t is just the projection onto the x-axis. T sends this to the vector x0. So any vector under this operator t is projected onto the x-axis. Why is this linear? Suppose v is xy and v prime is x prime y prime. Then v plus v prime, when you add them, you get x plus x prime, y plus y prime. So t of v plus v prime is the first coordinate. It's t of x plus x prime, y plus y prime. That's x plus x prime, 0, which is the same as x0 plus x prime 0. And x0 is t of xy, and x prime 0 is t of x prime y prime, which is t of v plus t of v prime. So the first property of a linear transformation is satisfied. And t of c times v is t of c times the vector xy. That's t of the vector cx cy, which is cx0, right? Just replace the second coordinate by 0. This is c times x0, which is c times t of xy, which is c times t of v. So t of cv is c t of v. Here's another example. Suppose we take V to be R2. Suppose we take a matrix, a 2 by 2 matrix, A, B, C, D, and define T from R2 to R2 by matrix multiplication. By T of the vector XY is ABCD times XY, which is AX plus BY, CX plus DY. And you can check this is a linear transformation. You can do it explicitly, or you can just observe that if you take T of XY plus T of another vector, X prime, Y prime, let me call this matrix A. That's AXY plus AX prime, Y prime. But matrix multiplication is distributive in the sense this is A times XY plus X prime, Y prime, which is T of XY plus X prime, Y prime. So all of these calculations or verifications, they're somewhat tedious, but it's careful to be able to check them, and they're all worked out very explicitly in the text. By the way, calculus is full of linear transformations. So suppose we let V be the vector space of continuous functions on the interval AB. And we define a function I from V to R by I, maybe I is a bad letter. I'll just call it T. Because I sounds like the identity. By T from V to the R, by T of a function F is the integral from 0 to 1 of f of x dx. So you take a function, you do the definite integral from 0 to 1. F is continuous. Make this the interval from 0 to 1. F is continuous. So you can integrate it and you get a real number. And in calculus, you prove, spell calculus, right? Calculus. The integral of f of x plus g of x dx from 0 to 1, the integral of the sum is the sum of the integrals. This is t applied to the function f plus g, and this is t of f plus t of g. You also prove in calculus that the integral from 0 to 1 of c times f of x dx is c times the integral from 0 to 1 of f of x dx. This is t applied to the function cf, and this is c times t of f. So integration is a linear transformation. The set of all continuous functions on the unit interval is a vector space. If you add them, you get the sum of continuous functions is continuous. So is the product. And so integration is a lovely example of a linear operator that you've spent a year studying in Math 175 and Math 176. Another very important fact is that the composition of linear transformations is a linear transformation. So suppose we have vector spaces U, V, and W. And from U to V, you have a linear transformation S. And from V to W, you have a linear transformation T. And you can compose them. T composed with S is a linear transformation from U to W. So this is composition, which you studied a lot in calculus. The chain rule, for example, tells you how to differentiate a composite function. So I claim that if ST are linear transformations, then TS is a linear transformation. And how do we prove that? Well, TS applied to the sum of two vectors, U plus U prime. U and U prime are in U. This is T of, this is the definition of composition, T of S of U plus U prime, which is T of, S is linear, this is S of U plus S of U prime. But T is linear, so this is T of S of U plus T of S of U prime. This is TS of U, and this is TS of U prime. So the first criterion, the first condition for a linear transformation is met. And if I take the vector U and multiply by a scalar C, this is T of S of CU, which is T of C times S of U, which is C, I can take that outside because T is linear, C times T of S of U, which is C TS of U. So the composition of linear maps is linear. Okay. So let's look at some more properties of linear transformations, because actually the rest of the semester, all we're going to do is study linear transformations. So you have T linear transformation from V to W. So it's like, here's the vector space V, here's the vector space W, and T maps V into W. We can make a couple of quick observations, first of all. If I take the zero vector in V, T of zero, here's the zero vector in V. Of course, zero is the same as 0 plus 0. So T of 0 is T of 0 plus 0. But by linearity, this is T of 0 plus T of 0. And if I subtract T of 0 from both sides, I get that T of 0 equals 0. So if 0 is the vector, so I have the 0 vector in V and the 0 vector in W, and T maps the 0 in V to the 0 in W. Suppose sitting inside of V, I have a subspace, V prime. So let V prime be a subspace of V. And let T of V prime, which we call the image, sorry, I don't call it that, I don't even could, but T of V prime is the set of all vectors W over in W, such that W equals T of little v prime for some v prime in the subspace. So if I take, this is my vector subspace v prime. If I take any vector v prime in here, it gets sent to something, t of v prime over here. All of that is what we call t of v prime. And there is a lemma, theorem, whatever you want to call it, that says t of v prime is a subspace of W. So if I take V prime and I look at take all the vectors in there, look at their images over in W, that's what I'll call T of capital V prime. That's a subspace of W. And the proof goes as follows. What does a subspace have to have? It has to contain the zero vector. It has to be closed under vector addition, and it has to be closed under scalar multiplication. So the V0 vector in W is T of the zero vector in V. That's what I just proved. And the zero vector in V is in V prime. V prime is a subspace, so it must contain the zero vector. So this is in T of V prime. So T of V prime does contain the zero vector. Second, that W1, or that W1 and W2 be in T of V prime. So that means that then there exist vectors V1 and V2 in V prime such that T of V1 is W1 and T of V2 is W2. But V prime is a subspace. So that means V1 plus V2 is in W prime, which means T of V1 plus V2, which is T of V1 plus T of V2, which is W1 plus W2, is in T of V prime. So this set T of V prime is closed under vector addition. And C times W1 is in, C times V1 is in V prime because V prime is a subspace and is closed under scalar multiplication. So T of CV1, which is CT of V1, which is CW1, is in T of V prime, the image of the subspace. So if I take a subspace V prime of V and I look at look at its image over in W, that's a subspace of W. In particular, if I let V prime equal V, T of V, which is what we call it's called the image of T, is a subspace of W. So that's one important property of linear transformations. We also have what is called the inverse image of a set. So again, we have V, W, a linear transformation T from V to W. And if you have any set, let's say Y in W, we define the inverse image of Y in W by T inverse of Y. And that's going to be the set of all vectors V in V, such that T of V is in Y. So here I have my vector space W. I have some subset Y, not necessarily a subspace, but the inverse image is all the vectors V in the vector space capital V. They get mapped into Y by this linear transformation T. And the second part of this lemma, which is 11.4.7, if you're following in the book, as I hope you are, this is on page 236. It says that if W prime is a subspace of W, then the inverse image of W prime is a subspace of V. And again, the proof goes in 3 steps. So now we have a subspace W prime of W, and here is the inverse image of that subspace. It's all the vectors in V that T maps into W prime. So T of the 0 vector in V is the 0 vector in W, which is in W prime, because every subspace contains 0. So the 0 vector in V is in the inverse image of W prime. That's the first thing we had to show. Second, if V1 and V2 are vectors in the inverse image of W prime, then T of V1 is in W prime, and T of V2 is in W prime, by definition of inverse image. But W prime is a subspace. It's closed under vector addition. So T of V1 plus T of V2 is also in W prime. But because T is linear, T of V1 plus T of V2 is T of V1 plus V2, which means V1 plus V2 is in the inverse image of W prime. So if I take 2 vectors in the inverse image, their sum is in the inverse image. Finally, if V is in the inverse image of W prime, and C is a scalar, say a real number, then T of V is in W prime. And W prime, again, it's a subspace, so it's closed under scalar multiplication. So C times T of V is in W prime. But C times T of V is T of CV. So CV is in the inverse image of W prime. And that's the third and last thing I needed to check, that the inverse image is closed under scalar multiplication. I just showed is closed under vector addition. It contains the 0 vector, so it's a subspace. There's one more important subspace associated with the linear transformation, and that's something called the kernel. So again, we have V, we have W, this function T from V to W, what is called the kernel of T. It's all vectors V in the vector space V, such that T of V is 0. That is, here's the 0 vector in W, and we want to find all the vectors V that get mapped to 0. And I claim this is a subspace of V. This is lemma 4.8. Well, we know, so this is proof. First of all, we know T of the 0 vector in V gets mapped to the 0 vector in W, So the 0 vector in V is certainly contained in the kernel of T. How do we know the kernel is closed under vector addition? If V1 and V2 are in the kernel of T, then what is T of V1 plus V2? It's T of V1 plus T of V2. But V1 and V2 are in the kernel, so each of these is equal to 0. And 0 plus 0 is 0. So V1 plus V2 is in the kernel of T. And finally, if V is in the kernel of T, then T of C times V, for any scale where C is C times T of V, is C times the 0 vector, and anything times the 0 vector is still the 0 vector. So C times V is in the kernel of T. So the kernel of T is closed under vector addition, scalar multiplication, contains the 0 vector, and we're done. So again, let's look at our picture. Here's V, here's W, and a map T from V to W. So sitting inside of W, we have a subspace, which is the image of T. It's all the vectors in W, which are images of some vector in V. That includes the 0 vector. And sitting inside of V, we have a subspace, which is the kernel of T. And every vector space has a dimension. We define, so these are two definitions. The nullity of T is the dimension of the kernel of T, and the rank of T is the dimension of the image of T. So if V and W are finite dimensional vector spaces, these are finite dimensional subspaces. The kernel has a dimension, the image has a dimension. And let's look at an example. Let's take the simple example of projection onto the x-axis in R2. So suppose we define the function t from R2 to R2 by t of xy is x0. So the image of T, it's all vectors x0 for any x. This is the one-dimensional subspace, because x0 is just x times 1, 0. This is the one-dimensional subspace spanned by the vector 1, 0. So in R2, this is the image of T. It's the x-axis. And the kernel of T, it's all vectors xy, such that T of xy is 0. It's all vectors xy. What is T of xy? x0 equals 0. So this is all vectors xy, where x is 0. In other words, it's all vectors 0, y, or y times 0, 1. So what is this? 0, 1, that's the unit vector on the y-axis. So the y-axis is the kernel of T. And in this case, we see that the dimension the rank of T, which is the dimension of the image of T, is 1. And the nullity of T, which is the dimension of the kernel of T, is 1. And there's a famous theorem that says 1 plus 1 equals 2. So in this case, the rank of T plus the nullity of T is 2, which is the dimension of R2. That's nice. Let's look at another example. R2 is easy to work with because you control it. Suppose I have T from R2 to R2 defined by T of xy is yx. So, for example, if you take 2, 1, it goes to 1, 2. What is T of xy equal yx? If you look at a lot of examples, you'll convince yourself that this is really reflection across the line y equals x. When you interchange the coordinates, you're reflecting through the line y equals x. So the kernel of T, it's all xy, such that T of xy, which is yx, is equal to 0, which is what? Y equals 0, x equals 0. It's just the 0 vector. So for this linear transformation, the kernel of T is just the 0 vector. And what is the image of T? It's all of R2. Because if you take any vector like v equals 7 minus 3, T of minus 3, 7 is 7 minus 3. In general, T of yx is xy. The image of T is all of R2. So all of R2 is the image of T. What is the rank of T? It's the dimension of R2, which is 2. What is the nullity of T? It's the dimension of the 0 vector, which is 0. The vector space just consisting of 0 has dimension 0. And again, 0 plus 2 equals 2. Rank plus nullity is 0. Okay, so I'm going to talk about this a lot more on Wednesday, but the kernel and the image of a linear transformation are important and worth thinking about. Okay. And that is all we can talk about today. Bye all.